Now let's try some exercises with electric field lines. Let's start with some very basic review. Here we've got a positive charge. What direction would the electric field lines be pointing in this electric field? Well, since this is a positive test charge would move away from it. So our electric field lines are going to point radially outward from our positive charge. Do you remember what this distance here means? This distance is proportional to 1 over r squared, which means that our electric field strength is decreasing as the radius is increasing. Electric field strength is represented by the distance between electric field lines. What if we've got a negative charge? Can you draw the electric field lines in this case? Let's draw them together. A positive test charge would move towards our negative charge here, so our electric field lines must point toward the negative charge like this. Again, these lines are pointing radially toward the center of the charge. What if we've got something like a spherical conductor? Let's say it's got a bunch of electrons on it. Where would these electrons reside? Well, since this is a conductor, we know the charges are free to move, so the electrons will try to get as far away from each other as they can. This means that the electrons will all be on the surface of our conductor. What does this mean for the electric field? Why don't you pause the video and try to draw some electric field lines? Alright, if you said that the electric field lines outside the conductor look like this, you're exactly right. The positive charges would be attracted to the center of the conductor, so we've got radial electric field lines pointing inward. This is a lot like what you would see for a negative charge, just a point charge. How about inside the conductor? What is our electric field going to look like? As you might remember, by the principle of superposition, we'll see that the electric field inside the conductor is 0. This is like a Faraday cage. What if we have a nice, evenly distributed charge in some kind of insulator, like this slab here? Let's say we've got positive charge evenly distributed throughout the slab. What sort of electric field would you see on either side of the slab, here and here? Why don't you draw it out? Alright, let's think about this. If we've got positive test charges down here, they will all be acted on in the same direction, like this. That means our electric field is going to be uniform, and it will point away from the slab because the slab is positively charged, so positive test charges are driven away. What if we have an electric dipole, a negative charge and a positive charge some distance apart? What would the electric field lines look like in this case? Remember to think about superposition, in this case adding up the electric fields caused by the 2 point charges. Why don't you pause the video and draw this out? It might take you a minute. Let's think about this together. A positive test charge will be driven away from the positive charge and attracted to the negative charge. From any point in space, we'll see that this is true. First, this charge experiences a force going away from the positive test charge and then pulling it toward the negative test charge. So, we'll see symmetry as well. So you'll get an electric field that looks a lot like this. Remember to include field lines that are coming off the page as well. This one is going to be our trickiest example. So if you got this one right, good for you. With that, I'll be moving on to our next lecture.